Right. For 1.67, for written in rule of inference order, all men are mortal, and Socrates is a man, hence Socrates is mortal. And we ask, okay, is this valid or not? Right? If it's valid, we're going to have reasons that go through it. Now, this one here, all men are mortal, right, is logically the same as what particular thing? If I would look at this and say, all right, all men are, I have two propositions. When you have the word all, you know that this is going to be a quantification of some sort. And so we have all men are this. So when we look at that, we would say, okay, I see two predicates. I have being a man, being mortal. Now when we had the two predicates, we had those four things that I wrote that one day where it was like, okay, everybody is predicate 1 and predicate 2, or all is predicate 1 implies predicate 2, or there exists. Everybody remember this? And there exists predicate implies predicate. Remember, we had one homework problem that talked about the four of these, and we asked which were the two most common. The two most common were this one and this one. What is the first circle? For all possible people, right? If they're the first predicate, then they are the second. That was that whole all of the first are the second, right? Which would actually say that that's what that one's talking about. What is this second one here? What does that talk about? Someone has both, right? That'd be like if we were talking about men and mortal, some man is mortal. What would this one be up here? What would be that top one?
For all men, they are.
Right, all men are mortal, right? Actually, there'd be all people, actually this way. All people are men and mortal. So that would be, we would be throwing away, there's no immortal men and there's no women, right? And so the first one, the very top one says, everyone of the entire planet is a mortal man. The second one says, well, if you're a man, then you're mortal, which is to say all men are mortal. The third one says, there is some mortal man on the face of the planet. And the last one says, same thing, which would be true, except what if we had no men? It would still be true. So for us, in terms of logical equivalencies, this is one that's important. Recognizing that when we have all of this are this is always going to be of that second type.
So I think what I was doing was, for all x, which x was men.
Right. Yeah, but it wouldn't be men. It would be.
So
we need an implication, right? We need
like precisely what they say. You
can. No, we're taking. I'm taking exactly what they say. I'm saying this: for all people, if this person is a man, then this person is mortal. Okay? That's what that first one says. What does the second one say? Man, Socrates. Socrates is a man. Hence, what does this last one say in notation? Mortal is Socrates. I suppose I'm talking like Yoda. Socrates is a man, yes. Socrates is mortal, yes. Socrates mortal. All right, is this true or not? No laws of inference can be used yet, right? None of these rules of inference can be applied. But I can do something. For example, for all people on the planet, it's true that if they're a man, then they're mortal. That's what that first line says. If that's true for everybody on the planet, would that be true for me? Yes, if Mark is a man, then Mark is mortal. Is that true for John? If John is a man, then John is mortal, right? Is it true for Socrates? If Socrates is a man, then Socrates is mortal. That would be what? if it's true for everyone, if I pick one particular example, why do I pick Socrates? Because who am I talking about? Socrates. I wouldn't pick Mark. It would still be valid, right? That's called universal what? Instantiation. Pick an instance. And so what I could then say is, by universal instantiation with line 1 would say this. That denotes man Socrates implies mortal Socrates. Okay, is everybody okay with that? That's universal instantiation. What's line 2 still? Line 2 is still is man Socrates, right? That's still line 2. It hasn't changed at all. But now look at this. Man Socrates implies mortal Socrates. I have man Socrates. Socrates is a man, right? Now what could I use? Modus ponens. What am I supposed to affirm? The hypothesis. What am I affirming? The hypothesis. That's modus ponens, right? And so hence, right, I could say by modus ponens, or you could say affirm the hypothesis, I would have mortal Socrates. And so what you would have is back here in the original problem, all men are mortal, Socrates is a man, hence Socrates is mortal. By universal instantiation, if all men are mortal, what I've really said that is if Socrates is a man, then Socrates is mortal. That would be universal instantiation. I was talking about Socrates. But Socrates is a man. Oh, okay. By modus ponens, affirming the hypothesis, therefore, Socrates is mortal. So this is valid by using universal instantiation and affirming the hypothesis. Is everybody okay with that? So those are the two rules of inference we used. Now, some people would give this argument and do things like this. All men are mortal, hence Socrates is mortal. They would leave off the second line, and they would leave off the second line would be, oh, well, I know who Socrates. Do you know who Socrates is? Yes, he's a man. You're supposed to know that. That'd be anthematic. Sometimes you can leave off entire premises. Just saying, everybody knows who Socrates is. And somebody goes, well, wait a second. My professor in the psychology department has a cat that he brings to class called Socrates. Is that what you're talking about? It's like, no. It's like, why do you think he has a cat called Socrates? So you have to kind of be careful. Enthymemes tend to be cultural. It's like, everybody knows that. And everybody's like looking at you like, what? And then it's like, oh, I guess I'm old. You don't know. Is that okay? Now, one of the things about going through rules of inference is, correct inference means you have used a tautology. All right, there's two common mistakes that everybody does. All right, correct is things like P implies Q. Again, who are you supposed to affirm? The hypothesis or the conclusion? You're supposed to affirm the hypothesis, and therefore the conclusion would follow. Okay, again, this is modus ponens. I'll kind of use this interchangeably with affirm the hypothesis because I want to say who you're supposed to. Yes?
I had a quick question. Like last class, you briefly showed another way to rewrite some of these, and
using logical,
using logical
equivalencies. that you could
Yeah.
do a modus ponens. A modus tollens is a modus ponens.
Yeah.
Yeah.
Yeah, but no, I think maybe it was slightly different. Like you had P implies Q and P in parentheses.
Resolution, which is like an implication with ors. Yeah.
Oh, okay.
So yeah, all of those. If it's a tautology and you have all of these logical equivalencies, you can play around with it and say, okay, this is valid, right? And so we have things like modus tollens, which is the idea of deny the conclusion. Therefore, you can deny the hypothesis, right? These are all valid. Okay, a hidden version of it, like if we put it this way, modus ponens in a new package would look like this. Not P or Q, I have P, hence what? This is a fun headache. All right, is P implies Q the same thing as not P or Q? Right? Well, modus ponens tells me that that's still modus ponens. But it's one of those ones where a person might sit there and go, what? All right, I don't have a phone or I have keys, if that's what I said. I don't have a phone or I have keys. By the way, I have a phone. Okay, you have keys. And you're kind of looking at that, it's like, what? That's modus ponens. It's just modus ponens in a new package, right? Because implication is the same thing as not P or Q. Now, it might be one that make your head will sit there and go, what? It's like, well, maybe if I give you the not P or Q, you should just write it as a P implies Q, and modus ponens seems a little bit more natural than the disjunctive form. But you could use the disjunctive form. You also could do things like, well, what if I had, these are all modus ponens. I'm just playing around with that whole not P or Q. What if I would take that this is not, I have P and I don't have Q. By the way, I have P, therefore I have Q. Okay, let's go back to the phone. You know what? It's not true. It's not the case, if this is actually true. It's not the case that I have a phone and I don't have my keys. I have my phone. What does that tell you? I have my keys. Now that seems a little more natural. If I came in here and said, you know what? It's not true that I'm going to have my phone and not my keys. That's not true. By the way, look, I have my phone. What does that tell you? I have my keys. That seems a natural thing, just like the implication does. All of those are modus ponens. They're just using logical equivalencies to state it just a little bit differently. So we have to be careful, like when we have it, they don't necessarily have to jump out saying this is modus ponens. So sometimes you might want to rewrite it as an implication until you get an implies, right? Now, all of these are valid, right? If all these are tautologies, you can have the classic look of modus ponens, the classic look of modus tollens, or using logical equivalencies, a repackaging of modus ponens and modus tollens. But we have to be careful in that sometimes people go through these problems and do something that is a contingency. If a person takes a contingency, what is a contingency? Sometimes true, sometimes false. It's not a tautology. That's the important part. Right? It's sometimes true, sometimes false. And put the word and in pass. And act like or use it as if it is a tautology. If you do this, the thing that you just used is normally called a fallacy. A fallacy is something that's not a tautology and you're acting like it is. It's kind of like the idea, if it's a common mistake. It's like, oh, look, this is a tautology. No, it's not. Oh, it's a tautology. You're right, you've said this 3 times in a row. It's a fallacy. I'm going to give it its own name. You keep doing the same mistake over and over and over again. It's not a tautology. Well, fine. If this keeps showing up, we'll give it its own name. We'll call it a class of mistakes, and we call them fallacies. So what is a fallacy? A fallacy is just a mistake that shows up all the time where it's of the class of, hey, look, it's a tautology. And it's like, no, it's not. Now, where do fallacies come from? All right, here's our first one. P implies Q. What am I supposed to affirm? The hypothesis. I'm supposed to affirm the hypothesis. Right? And instead of doing P and Q, I'm going to do M and B. And I'll explain why here in a bit. M implies B. I'm supposed to affirm the hypothesis. Therefore, I would have the conclusion. This is correct. Right? Nice little blue. That's good. All right, but what if a person says, you know what? They just get their head turned around. M implies B. What are you supposed to affirm? You're supposed to affirm the hypothesis. But they decide to affirm the conclusion. And then they say that I therefore must have had the hypothesis. And what have they done? They have done it backwards. So if you had to give it its own name, you would call it the fallacy of affirming the conclusion. You're supposed to affirm the hypothesis. You just affirm the conclusion. That's a fallacy. And so we call this one the fallacy of affirming the conclusion. All right. M implies B. Who are you supposed to deny? I'm supposed to deny the conclusion, and therefore I would not have the hypothesis. This is a good thing. This is correct. Okay, but let's say somebody gets it backwards. M implies B. Oh, wait, I'm going to deny M, and therefore I will not have the conclusion. Again, they've denied the wrong thing. This is bad. This is the fallacy of denying the hypothesis. They've denied the opposite, right? Why did I pick M and B? Because the classic example, it's always fun to do, is being a murderer with bloody hands. If I'm a murderer, then I have bloody hands. I'm a murderer, and I walk into class, what are you going to see? Bloody hands, right? That is a correct use of inference, right? You have affirmed my murderingness. You're a murderer, and I got bloody hands. All right, what about the other way? If I'm a murderer, then I have bloody hands. I don't have bloody hands. What do you know? Not a murderer. That's a correct use of denying the conclusion. But now somebody flips it, and it seems very natural. If I'm a murderer, then I have bloody hands. I have bloody hands. What does that tell you? Well, somebody says, well, you're a murderer. Because if you're a murderer, no. I fell on the way to class. I have bloody hands. What's your point? I just scraped my hands up. Why does that make me a murderer? What did you do? You affirmed the wrong thing. That's a fallacy, even though it tempts you to do it. I walk in here with bloody hands, and you're like, oh, murder. It's like, what are you talking about? That's a fallacy. Okay, I walk in here and I say things like, if I'm a murderer, then I have bloody hands. By the way, I'm not a murderer. And then you look at my hands. Well, they better not be bloody. Well, it's like, that's what you say. But it's like, no, they're bloody. It's like, no, you've used the fallacy of denying the hypothesis. I fell on the way to class again. I'm really trippy today. Is everybody okay that it's tempting to use those, but they're not tautologies? There's other things that can happen that make you have bloody hands besides murdering. Is everybody okay with that? And so these are very, very common. Common mistakes that show up all the time, if they show up a lot, are called fallacies. And if you do it so often, you actually give them their own type of fallacy name. Yes?
Would they work if it was a biconditional? Yeah, they would, right?
We'd have to, let me sit here. That they're logically the same. Well, we'd have to do that. I won't say yes because I don't have it yet. You're telling me that if M, if and only if B and then you have M, and you're telling me hence B, right? Because what is that? That is M implies B, and B implies M, and you have M, right? That would mean that I could just simply completely ignore that, use affirming the hypothesis, and then get a true conclusion of B. So, yes. And the same thing would happen if I would have B. I would also get M, because that would be the same thing. If that's a B, then I would use this one and ignore that one, and also get AM. So the yes, but why? The biconditional is two implications, and those two implications are in opposite order, and therefore it's whatever you have as an assumption is going to be a hypothesis of one of them, and then you would use modus ponens.
So it's
Like a lot of those, they aren't just, oh yeah, it is. It's like, time out. If you can show it, you have to show it, right? So you have to give me the rules of inference that allows it to be valid. So yeah, and that's kind of interesting. Sometimes there's things that say, boy, it feels intuitive. Some of the logical intuitiveness that you have, like that one, is correct. Sometimes there's things that feel natural. I walk into class with bloody hands. And a natural question of, well, wait a second. If he's a murderer, then he has bloody hands. He has bloody hands, you know. And the natural thing is to start freaking out. And the answer is like, no, there can be other things. It's a contingency. And you have to be careful. Sometimes it leads you right, and sometimes it leads you wrong. All right. For all of these forms of reasoning and rules of inference, we're building up to 1.7 and 1.8, which we're going to have for the next 3 classes. And these are all proofs. All right, what's the idea behind what I want you to know from these particular sections? The idea behind proofs is, the first thing I'm going to have to talk about is the axiomatic theory. Okay, all science is based on this. And it's one of the things where we sit on, when I've ever heard people and they're having arguments of any sort in terms of man, or I think, is that in here? Sometimes I've given this one. 1.6, is this valid reasoning? Did they get rid of it? Used car salesman, rules of inference. I think he pulled it. Oh wait, no, 35. Do I sign 35 for you in 1.6? As homework? I don't remember. This is a classic issue in terms of the idea of going through reasoning. This one here, 35, is a star problem, but it's actually not that bad if you dig through it. If Superman were able and willing to prevent evil, he would do so. If Superman were unable to prevent evil, he would be impotent. If he were unwilling to prevent evil, he would be malevolent. Superman does not prevent evil. If Superman exists, he is neither impotent nor malevolent. Therefore, Superman does not exist. That was kind of a rewording. It's like kind of like people throw this out sometimes, it's the non-existence of God proof. And we get through these arguments that people have on particular things. And it's like, no, we have to be able to show it and reasoning and everything else. And I always find that kind of amusing, especially with the idea of the axiomatic theory. For like that one, you have to assume that as you go through that, the only way this could be a valid argument, by the way, that's a valid argument, if you assume the premises to be true. Right? But there's one premise in there that if you've ever been a parent, which is if you're unwilling to, for example, prevent evil, you'd be if you're unable, you're impotent, but if you're unwilling to prevent evil, he would be malevolent. And it's like, if you think about evil, and a lot of people think about times of harm, as a parent, have you ever had a kid, or like as you grow up, what do you do as a parent? It's like, I don't want bad things to happen to you, but I'm going to let you. I think the best example is hot stove. Right? You can tell a kid, don't touch. They come back up, they try to touch. Don't touch. They come back up, don't touch. Right? They keep trying to do it. All right? So I had a friend that it's like, okay, he turned it to where it wouldn't burn them, but it would hurt. And he knew they were going to try to touch it, so he was working on the stove, and he just kept working on the stove. They touched the stove. It hurt, at which point they never touched the stove again. Right? Now, did that make him malevolent? So that makes that one premise what? Not always true. And so that's a question. When you go through these things, you have to go through and think long and hard. Is this premise right or not? All right? Now, the same thing is true when we're going through any form of reasoning. You have to think hard about certain things. What's amazing to me that you used to think, like I was like mathematics, and I liked math better than other things, is because you would just simply, okay, we got this, and no doubt, you have these nice little building blocks. At the very bottom of all reasoning, below everything else, are two things. One, these are things we must accept. Undefined terms. All right, these are terms that just simply, they are, which might make you scratch your head and like, well, what do you mean? Like one or point. We all agree the idea of one, like one pen, one piece of cloth, it's just, but please define what that means. If you try to define it, you run into a fallacy of what's called circular reasoning. So you say things like, well, one is one, which is one, which is one, which is one, which is one. It's like you just said it a bunch of times. You haven't defined it for me. When we start to go through reasoning and we have discussions, we have to have a beginning. And the beginning of terms are just things that are. Like point, one, I think, he did it. It was talking about science, and God gave us one, and then we built everything else after that. I think it was physicist. He can't speak anymore. Hawking's, right? It's just, you have to have a beginning. Not only do we have a beginning with terms, we have to have what's called axioms or postulates. These are propositions that are true by definition. They just are. A classic one on this is the division point of geometries. Example, I have a point, I have a line. Given a point and a line, we can ask a particular question. How many parallel lines? It ends up that the answer to this particular question is an axiom, not something that can be shown. And you can actually go through it, and if you pick different answers, you will form completely different geometries. So you have to have a beginning of some sort. So if I say there is exactly one line that goes through that point that is parallel to the line I drew, that would be a line on two-dimensional space that's infinitely flat. That's called Euclidean geometry. But if somebody says that, I believe that there are no such things as parallel lines. All lines will cross. If that's your postulate, then your geometry is no longer geometry on a flat plane, but it's a geometry on a sphere. Because if you would have points on a sphere, all right, what's a line? Well, that's the shortest length between these 2 points. And so when people say things like, well, if I'm in Chicago and I want to fly to say, Japan or Korea, people say, well, go west. No, go north. You sit there and you look, well, yeah, you're thinking maps are flat. The shortest distance between 2 points is a grand circle. It's a circle around the entire Earth that has as its center the center of the Earth. So if you have this sphere and you look between these 2 points and you say, if I would have a grand circle, it would be the one that would go up around the North Pole and then come back around. and that would be the shortest distance. And if you would have all such lines, imagine all grand circles. They cross, right? That's it. And you also have lots of really fun things, like in Euclidean geometry, because of this, the internal angles of a triangle add up to what? 180 degrees. On a sphere? Nope. That's not true. Well, what if I say there's an infinite number of parallel lines? If that's your postulate, well, now we're in hyperbolic space. And now there's some questions like, do you think we live in a Euclidean space? Do you think we live in a spherical space? Do you think, which is elliptical space? Do you think we live in a hyperbolic space? Because space is space. But which of those types of geometries have which postulate that we're talking about?
What about the other axioms? Do you get rid of any of them in this system?
And you start to, there's lots of different geometry. There's taxicab geometry. There's lots of things that we can play around with. And geometries are the fun ones because it allows us to really strongly understand that create different fundamental assumptions creates different mathematical systems. But it ends up being that you don't have a choice. You have to have assumptions. You have to have things that are. These are true, these are. Then we build. So these must be the basis of everything. Just things that we have. That they're just given. All right, now that we have things that are just given, we build from that particular point. The axiomatic theory basically looks like this. Down at the bottom, it's an upside-down pyramid. Down here at the bottom are we have axioms. Obviously below axioms, we'll have terms that we're using on them. We'll have undefined terms. Then built up above this, once these are given, what we're going to do is stack up above this are propositions we can show to be true, and terms we can define. The show part is what we're interested in 1.7 and 1.8. What do I mean by show? I want to simply say that there is a mathematical argument that's valid that demonstrates the truthness of the proposition. So what we're going to look for is a valid argument that demonstrates the proposition to be true. All right, what are some terms that we can define, all right, about these ideas? And this particular thing is simply going to be called a proof. So a valid argument that demonstrates this thing that you were talking about, you can show me that, you can give me a valid argument for it? Yes. That valid argument is going to be called a proof, and it's going to get a new name. So what are some terms that we have for it? Terms. All right. First term is the idea of a conjecture. A conjecture is simply a proposition you think may be true. All right, what was said here at the beginning? Like, well, what if we use the biconditional instead of an implication? Is it going to be a valid argument? That's a conjecture. Right? It's like, I think it's true. Now, conjectures are rather interesting. There tend to be people who are just natural at them. Fermat was an armchair mathematician who read math books, and in the margins of the math book, he would write down little notes, and then he would write letters to actual, like famous mathematicians. Oh, I think this is, and he would have little things back and forth. And after he died, his son took all those notes and published it. And Fermat was just one of those guys that just simply had great conjectures. He could usually see things. He couldn't show it, right? But he had a leaping ability that most people did not. And one of those things was, for example, on this one. Say x to the n plus y to the n is equal to z to the n. He was reading a book that was talking about the Pythagorean triples, which is to find things like 3 squared plus 4 squared is equal to 5 squared, and trying to create generators that'll generate all Pythagorean triples, which will solve, the right triangle and, equality. Sums of the squares of the sides is the square of the hypotenuse. And it was like, it was going through, we have generators, generate all possible ints that would ever do this. There's an infinite number, but you can make them, besides 3, 4, 5, right? So there's other things that would make that true. And then what he wrote in the margin of his book was, you know what? If the power instead of 2 was like a 3 or a 4 or a 5 was bigger than 2, it has no answers. Which kind of makes you scratch your head. It's like, wait a second. If it's squared, there's an infinite number, and here's this entire thing talking about generating all these infinite number of things. But you tell me if it's a cube, no ints will work. If it's a fourth, no ints will work. And he says, none of them work. And he goes, and I thought of a wonderful proof, but it's too big for the margin of the book. And he died, and that got published, and mathematicians read that and thought, really? And we spent hundreds and hundreds and hundreds of years trying to, did he have a proof? He most likely didn't, because he was a good conjecture person, but he wasn't, great. But he was right, and it wasn't proved until around after 2000. And the mathematician, it's a really good, if you read Nova for PBS had a special on it called The Proof. Look it up. I think it's on YouTube. And watch that. It's pretty amazing. It's like it was like 100 and some pages, new mathematics with only the last 100 years what had to be developed. And it didn't, the proof of this was by the way, because this bigger thing is true, that's true. So it ended up being a special case of something larger. And so conjectures are amazing things because a lot of times they make new mathematics. I think this is true, and then we grind and grind. I wonder, we develop things to try and figure it out. Do new tools, new types of systems, things to work out those problems. So conjectures are the things that drive PhDs in math, masters in math, try to do different things. Now, if it is true, we move on to if you can show it to be true. If it is true, basically that means that you show it, not just simply assume it. But it ends up being that sometimes like the parallel postulate, like for Euclid said there's one line, and people said, man, it's a complicated postulate, and they kept trying to prove it and prove it and prove it. It ends up that you just have to assume it, right? But if you can actually show it, it then becomes, well, different terms. We give them different names. Proposition, a lemma, a theorem, or a corollary. These are all the same thing, and then we will call it one of those. Proposition, a lemma, a theorem, or a corollary. All right, why do we use different words? Theorem is the big word. Is it important? Does it hold great significant meaning for mathematics? Let's call it a theorem. Is its main purpose to show something that's more important than it? Right? I created it as a smaller tool to make a bigger thing. If that's true, we call it a lemma. A lemma's sole purpose is to show something bigger than itself. Right? I have to prove this I have to get to step 1 to get to step 2. And step 2 is super important. So step 1 I'm going to call a lemma. Step 2 is going to be the theorem. On the other hand, is this a statement that's obvious from this bigger thing? So like I talked about Wiles, right? He proved a much bigger theorem. And by the way, a corollary, which is a natural byproduct of it, is this special case. And so you do something huge, and it's like, oh, look, isn't this a natural result? Yes, that's a natural result. If I use that to show this, it's natural, and so it's a corollary. Yes?
You even have like the big one, right? Like the fundamental theorem of algebra. Or
Yeah, we'll even call things like fundamental. Yeah, it's like, so it's not only is it a theorem, we consider it like the so there's fundamental theorems of arithmetic. There's fundamental theorems of algebra. There's fundamental theorems of calculus. It's like, this is so important. We'll even call it fundamental. But it's still a theorem. Okay, what's a proposition? It's a throwaway thing, right? Prove this. It's your homework. What's the homework? If it's true, those are all propositions. right? It's just one of those things where, let's do something. Hey, look, it's true. Wasn't that neat? It's a proposition, right? It's not that important. It's a building block to learn how to do things. Is everybody okay with why we would pick different terms? It's really just a measure of importance. I suppose we could call everything a theorem. That means that'd be like the everybody gets a first prize for showing up. So, all right. And we're going to use proofs to show these. So let's go into types. Things to prove. All right, we're going to break the things to prove into particular types. The most obvious first type, say type 1, is you have proposition is something implies something, right? If this, then this. This is kind of like a natural form of a proposition. So, example. If a number is odd, then its square is odd. That's my proposition. I believe that if you take an odd number and square it, you're always going to get an odd number. So they're like, okay, you're telling me that if you take an odd and you square it, you get an odd. All right. If I'm going to show this, we're going to go to proof techniques. There's different techniques to show things. The first technique that we're going to talk about is the idea of a direct proof. A direct proof is one where, okay, this is implication, right? Of an implication. What happens if the left-hand side is false? What is the proposition going to be? It's just vacuously true, right? And so that would be called a vacuous proof. A vacuous proof would be this. You told me that if a number is odd, then its square is odd, right? Well, what if I said it's like, if an integer looks something like a odd divided by 2, then, and it's like, wait a second, an odd divided by 2 is never an int. Okay, then I'm telling you the truth. Vacuously, right? Now, on the other hand, if we would say something like this, if, doesn't matter whatever you say, implies, and I say something that's just plain true. If a number is odd, then my name is Mark. All right, your name's Mark. Yeah, that's trivially true. Right? Anything implies true is true. False implies true is true, right? So those are the two most obvious we could toss out. Is the if false? If it's always false, it's just, okay, the proposition is true because it's vacuous. It's empty. If the answer is true, if this, then your name's Mark, but your name's Mark. Okay, that's trivial. I didn't need the implication. It's just true. All right, something more complicated than that would be these. And so we'd have, okay, the other opportunity is I need to show that only line 1 exists, right? Because the vacuous, we don't have to worry about. I want to show that if the left is true, then the right must follow. That's the idea of a direct proof. The idea of a direct proof is to go through this and say, all right, I'm going to go ahead and assume that the left side is true, and then I'm going to show that the right-hand side must be true from the left. Because the left was true, the right must be true. What I've really showed is because the left is true, it's impossible for the right to be false. And that's the only time that a proposition of this sort, that's almost a tautology, right? The only time it's false is if I have true implies false. So what I'm doing is showing that true implies false is impossible. That's what I'm showing. Yep.
Is this modus ponens? Assume P implies, or
we assume that P implies Q. All right, and
we
well,
assume that P
no,
is-
because that would be assuming that the implication is true, which would be circular.
Oh, okay.
I'm not assuming that the implication is true. What I'm doing is, if the left-hand side happens to be true, there is a natural sequence of events that the right-hand side is also true. That means that the left-hand side being true is logically equivalent to the right-hand side being true. Does that make, like, let's take our example. Let's assume, so we're going to take this conjecture. I'm going to assume n is, and that's my number. That's a number, right? It's a universal question, so I'm not going to give you a number. Here's another thing. This is a universal question. It's just a number. Well, if a person said 3, well, what about 3? Well, yeah, 3 squared is 9, but you didn't prove it for all. How do I prove it for all? All. Don't put a number down. I'm not talking about instantiation. I need to show them all. Okay, a number is odd. What does that mean? What's an odd number? But what's the n? It's twice a integer plus 1, right? What are evens? Twice an int. All integers are 2 times an integer. All odds are 1 off of that, right? So assume that it is odd. But that's logically the same as saying that n is equal to twice, I'll just say an integer, plus 1. Is everybody okay with that? That's logically the same thing. Well, if n is equal to, I can now use algebra. Where do I want to go? I want to show that the right-hand side's true, but what's the right-hand side talking about? A square of that number, right? And so, well, that would say that, so n squared is simply twice this integer plus 1 squared. Everybody know how to square a binomial? Square the first, twice the 2 multiplied, square the second. But that's logically the same as n squared is equal to 4 times this integer squared plus 4 times this integer plus 1. A lot of times instead of saying int, you'd write k, right, to make it easier. You wouldn't use n because I already used n. What is n squared supposed to be? Odd. What do odds look like? 2 times an integer plus 1. Do I have that? I do if the underlying part is an int. Is it? What's an integer times an integer? An integer by the closure property of integers. Right? When's the only time we'd have a problem? Division, right? Or subtraction if we didn't allow negatives. But is 2 an integer? Yes. So we've got integer, 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 integer. Multiplication of integers is integers. Addition of integers is integer. So that entire thing is. So is the square twice an integer plus 1? It is odd. Because n is odd, n squared is odd. They're logically the same thing by using just simple replacements of equalities. So is it impossible for n to be odd and n squared not to be odd? Yeah, that was the whole point. True implies false is impossible. That's what I wanted. So I've now shown it, and so we're good. We are done. And normally, if you're done with your proof, I usually use a fill-in square. You can use QED, which is Latin for I did what I was supposed to do. You can look it up, and it's actually close to that. I think it's demonstrated what I set out to do. That's a direct proof. Assume the left, show the right. There's certain ones that are that when you get through proofs, for direct proofs, so later on next class we're going to move on to the indirect proofs and other techniques. We're also going to talk about combining several of them will have a lemma. One of the nice things is once you have a theorem, we can actually move some things out. So what I showed was, if I use a little bit of algebra, so I write it a little bit differently. N odd implies n squared odd was true, right? I showed that. But I can use things like, if that's true, is its contraposition also true? N odd implies n squared odd is logically the same as what? What's its contrapositive? It's not true that n squared is odd implies it's not true that n is odd. But for integers, there's only two types, even and odd. If you're not odd, what are you? Even, which really has said that this is the same thing as if n squared is even. That implies n is even. That's rather useful. That's called proving the contraposition. What if somebody asked you to do this problem? Well, you couldn't do it directly, but I could do that one directly, which is the same thing. That's called proving the contrapositive, which is just flip it. Take the knot of both sides. That one's kind of, if we think about the ideas of squares, if square being area, that means that you tell me, if you give me a square and you tell me its area, if the area of a square is even, what does it tell you about the length of the side? It's even too. And what does the first one tell you? Like here, if the length of a side is odd, then the area inside of it must be odd. And so we'll play around with all those different types. This one will be fun. This will be a lemma, that box right there, to proving the square root of 2 is irrational. Next class, we're going to prove the square root of 2 is irrational. Proving the square root of 2 is irrational will be on your first exam, and it's in the textbook, right? And so we'll actually go through that in the entire class. So go ahead and read ahead on that, as well as be ready to do it, because it's definitely on the first exam. All right, that's it. Attendance, 1.77. Attendance is 1.77. Sorry. Now we're done. Except hand your attendance in.